Okay, time's 2:30, so let's get started here. Project number 5 is due on Friday at noon. We will continue in chapter 5 today. Are there any questions? Okay, we left off last time on page 554. So we've been talking about ways to understand if there are any problems with your model. You know, we've looked at residuals and various like Pearson residuals to determine if there's some, let's say, poorly fit observation in your data set. We've also looked at overall measures of goodness of fit for your model. So for example, we did the deviance divided by degrees of freedom thing. And then we also looked at measures of influence as well. Now what we're going to do is take a look at a particular function that I've written in R that allows you to look at all those things simultaneously through some output that's generated by it. This function only works for binary regression models, so those are chapter 2. You can, of course, download it from my website. So we're going to look at it in terms of in the context of the place-kicking data set. So again, we need our data in explanatory variable pattern form, so I change it to that form the usual way. Then I estimate the model using the GLM function. The function itself is in my file examine.logistic.reg.r. That file is on my book's website. You can download it. Inside the file itself, you're going to see this. A whole bunch of comments about how to use the corresponding function that's in the file. And then you can see the function starting to be defined here. If I keep on paging down, eventually we get to the end of the function. So I wrote this function just to make your lives easier, because I think it really does a good job of summarizing the important aspects of these diagnostic measures that we've been talking about in section 5.2. To use the function, notice the very first argument corresponds to an object for your model's fit. So wherever you put the results from GLM, use that for the first argument value, and when using this function. Then I have another argument called identify points. What this function is going to generate is 4 plots, all in one graphics window. And you're going to be able to click on particular points to identify, well, what observation number they correspond to. This is going to be useful for you to figure out, okay, it will be useful for you to figure out, well, I see a point that's kind of outlined. Well, what observation does that correspond to? When you click on the point, the observation number automatically comes up. Also, there's going to be 2 of the plots are actually going to be bubble plots. We saw bubble plots back in chapter 2. Remember, it allows for a 3rd dimension, so that the plotting point itself is proportional to this 3rd dimension. And if I want a bubble plot, I say true. Notice the default value. Note the default value for identify.points too. 2 other arguments are scale.n and scale.cookd. We'll talk about those later. And then lastly, do you want plots involving the standardized Pearson residuals or the standardized deviance residuals? The default is Pearson. Okay. Please take a look at the function, the contents of the function on your own. It's basically taking the components that we've already looked at in terms of like the R standard function, putting it all in there, and then using the plot function to do our plotting. I'm going to get to my program here. So to tell R that I want to use that function, I need to get the function into R. What I could do is just simply highlight all this code in my examine.logistic.reg program and then run it. Or a little bit of a quicker way is to use the source function, which says, okay, go run the program that's at this particular location. So this is just a place where I have the program on my hard drive. I just specify it. I run source, and now that function that's in that program is available to me. In fact, all the code that's in that program was just run, even though you don't see any output corresponding to it. Any questions about that? Okay. To run the function then, examine.logistic.reg, I'm just going to specify my model fit object, and then for emphasis I put identify.points equal true. I save some of the numerical results into an object called save.info1. This is actually going to be a list that we'll take a look at shortly. Now let's look at what happens when I run this function. It's going to generate the plots on page 555. Okay, so as I said, there's going to be 4 plots produced. You only see one plot right now. It's a standardized Pearson residuals versus the estimated probabilities. Note that you have blue lines on there drawn at plus or minus 2 and 3 to help you identify potential, let's say, outliers. And again, remember we've talked about how even if I have a value that's outside that range, it doesn't necessarily mean that it's something to be concerned about, because our distributional approximations often don't work. But notice here my cursor. It's a plus sign, because it wants me to add something to the plot. In particular, what I can do is mouse over to where you see maybe some of the outlying points, the points that are outside the plus or minus 3 horizontal lines, and if I left click on that point, I will get the corresponding observation identified. So that means observation number 3 has a large standardized Pearson residual. Notice also I have an observation down here too. I'm going to mouse over to it and left click on it and look at its observation number 1. And I can go ahead, identify any points that I want to throughout the plot. Typically you only are concerned about the ones that are kind of outlying. Once I'm done with that, I right click, that brings up a little shortcut menu, and I say stop. Notice the lowest regression model is drawn on there in red to help us identify potential trend. Next, I have a new plot created here, Cook's distance versus the hat matrix diagonal values, also known as leverage. You see some horizontal and vertical lines there. Those correspond to the the limits that I essentially gave you last time about when we identify potential problems. So anything else, anything larger for like a Cook's distance larger than about 1.5 indicates maybe I have an influential observation. And notice there's only one point that's outside or above that Cook's distance horizontal line, similar with the leverage lines too. If I left click on it, observation number 3 pops up again. Once I'm done clicking on observations, I right click, stop. Then a new plot's generated. My delta x squared, remember that's a measure of, again, influence, just a different measure. And I plot that versus my estimated probabilities. Delta x squares that are larger than 4 or 9 indicate potential problems. Again, that's subject to the fact that our distributional approximation might not actually work though. And so we see 2 observations that are above 9. Number 3 and number 1, although it didn't really show up very well there. Now take a look at this bottom left-hand corner plot in relation to the one in the top left corner. They're basically showing the same thing. The bottom left one's on a squared scale. Remember, a standardized residual squared is the delta x squared. So we saw 1, if you see where my pointer is right now, you saw 1 and you saw 3, well, that corresponds to the 1 and 3 down there. Now the plotting point is proportional to the number of trials. Why do you think for a particular observation? Why do I want to do that? Because it looks cool? Why would I want to make the plotting point proportional to the number of trials for a particular observation?
If an observation has more trials, then that might be influencing why it's, or less trials that might be influencing why it's.
Kind of. I'm looking more for an answer corresponding to some stuff I said about a minute ago about probability distributions. Yeah, any kind of distributional approximation might not be reliable for small observations. So this, I'm sorry, a small n. So a small number of trials for a particular observation. There, I think I got it right there. So, you know, and we've seen this before. Remember observation number 1. That was for 18 yards, 3 trials. And there just so happened to be 1 failure. And we said that, okay, that's probably why, you know, the standardized Pearson residual is coming up to be so large. Also because pi hat was extremely large for 18 yards. And so because of that, I know that this distributional approximation is not going to work well. So I'm not really concerned at all about observation 1. And so by having the plotting point proportional to the number of observations per, the number of trials per observation, that helps you see that. Now, in this particular case, notice we have one circle that's very large. That's the 20-yard place kicks, and that actually distorts the plot. We'll talk about how to get around that problem shortly. But what this is saying to me is that I have a standardized Pearson residual, or corresponding delta x squared, that is quite large, and is represented by a large number of observations. So this concerns me, as we've kind of discussed before. I'm going to just click on some more points here. Notice 5, 10, and 15. Notice how they all appeared right up here in the upper left-hand corner plot. Now they appear right there. Also remember how we discussed that with these, with this kind of a plot here with a delta x squared versus estimated probabilities, you typically see points that are up here. Also, we just don't have it in this particular case. When you get close to 0, you typically see points up here, and oftentimes they're not of concern. Sometimes they are, sometimes they're not. So I'm going to stop, and then I go to one more plot, exactly the same, but now I let the plotting point be proportional to Cook's distance. Now remember, in the upper right-hand corner plot, we saw one observation that really had a larger Cook's distance than all the other observations. Well, we see that represented in the lower right-hand corner plot by the big circle. So this allows you to look at, let's say, influence, 2 measures of influence exactly at the same time, essentially, the lower right-hand corner plot. So I can, again, identify those observations if I want to. And then when I'm done, click Stop. And notice at the very bottom of my screen here, I have my deviance divided by degrees of freedom statistic, 1.09. Remember, we look at 2 standard, or the closer to 1, the better for the model. We look at, well, is this statistic more than 2 standard deviations from 1? Or is it maybe even more than 3 standard deviations from 1? If it is, that indicates problems overall with the model. Here we see, yeah, it looks okay. So what we see from this plots then is that, hey, observation 3, we got some concerns about it. Okay. So let me go back here. So let's talk about how we can deal with this plotting symbol for observation 3 being so much larger than all the other ones. And it kind of distorts the plot. Well, if you remember in chapter 2 when we did bubble plots, we basically rescaled that third variable that we're plotting by. Remember, we were looking at a plot of the, well, actually I have the plot here. You just ignore my writing on it for now. This is where we saw a bubble plot before. Does that look familiar? Okay. And to counteract number 3, having so many more observations than all the other, so many more trials than all the other observations there, is that we basically rescaled the number of trials. You know, it was a vector of information. We rescaled it. So we use, I forget, maybe we use a log transformation. I don't remember exactly which transformation we use, but we rescaled it. And that's the purpose then of this particular argument here, scale.n. If I just have I there, that just corresponds to everything stays the same. If I put maybe square root or sqrt there, it will do a square root transformation of all your n's. There's a similar argument for scale.cookd for the bottom right-hand plot. So for example, if I do a square root transformation for the bottom plots, this is what I get. And you can see it helps a little bit, but you know, maybe I could do a little bit better too. So I thought, well, I played around with it for a while, and I came across the 1/4 root as working well. So take n to the 1/4 power, for example. And since there isn't a built-in function for that in R, I had to write my own function. And so then once I write the function, I say 1.4th.root. And now this helps out a little bit. And so what we will be looking for here is that, are there other observations that are maybe have a large circle? So for example, you know, maybe like 34 here, you know, comparatively to 5, 10, 15. You know, it seems to have maybe a little bit more influence than 5, 10, and 15 if I take into account Cook's D. However, notice it's not getting really above that delta x squared threshold. It's right about at it. Okay, so you know, once I do these plots, I come up with some judgments about my data or about my model. Often a good thing to do is basically put all these measures together into one data frame, and if you have a small enough data set, you can look at all your observations to help you get a better understanding of what's going on. So for example, while we've already seen this before, notice again observation number 1, you know, is coming up, you know, it's being pointed out in the plots. And we see it's a distance of 18 yards, 2 successes out of 3 trials. So again, I would not expect a normal distribution approximation or then a chi-square 1 approximation to work well here. And you know, if we hadn't seen this before, this could have been the first time that you saw, oh, okay, I'm not worried about that point because of what I see here in this data frame. But then, again, at 20 yards, I am worried. You know, I got a delta x squared of 13.16. But yet I still have 789 observations. 789 trials. Let's see here. Let's see, which one do we want to look at? Well, actually, let's go to the next plot first, because I think this is helpful, and then we'll go back to the data frame. So again, this is a plot that we saw from chapter 2, except for now I think I've written some red stuff on it that maybe we didn't see before. And so we see the big circle there represents number 3. Again, the circle is proportional in size to the number of trials per observation. And also we see number 1 there. Notice how small that circle is. And you know, leads us to the same conclusion that we've had before. But I think what's kind of cool to look at in this plot, and we used this plot at the time, was kind of an ad hoc way to overall get a general sense of how good our model's doing. And we said that if we had large circles that were far from the red line there, that's made a logistic regression model, that would concern us. If we had small circles that were far from the line, such as what we see for larger distances, that doesn't concern us. And so now relate this back to those 4 plots that we saw of those diagnostic measures. So for example, we pointed out that 5, 10, and 15 were kind of borderline. And maybe we should be concerned about them. And you can see that in this plot, they tend to have the larger circles that, relative to where they are in the red, next to the red line, they are kind of farther away. They're being pointed out. Look at where number 34 is. Notice that it has a little bit smaller circle than number 15 is, but yet it's maybe the same or maybe a little bit larger distance away. So let's go back to our actual data frame here. Let's see now. Which one is that? So let's take a look at number 5. So, 12 successes out of 14 trials, the standardized Pearson residual was negative 2.15. So it's a little bit outside that range. And so, what a normal approximation work here? Well, take a look. The estimated probability of success is quite high. 14, you would think, yeah, maybe. It's definitely better than what we saw for having only 3 trials. But of course, too, even if it did work, we realize that, yeah, about 5% of our observations are going to be outside of plus or minus 2. And this isn't too far outside of plus or minus 2. And if you look at all the observations, we only have, I think, 5 in total that are outside of plus or minus 2. So therefore, if I can trust my standard normal approximation, I'm not really worried. But I think it's also good to think about it this way, too, that maybe we can't trust the standard normal approximation, because just think if I had 13 successes instead of 12. What do you think would happen to that standardized residual? Is it going to get farther away from 0 or closer to 0? It's going to get closer, right? And do you think you're going to have a standardized Pearson residual outside of minus or less than minus 2 anymore? No. And so just because of one trial of those 14 wasn't a success, essentially, that's what's causing this. And all has to do with, in this particular case, the fact that we have such a high probability of success. So while you see 14 observations there, the number of possible successes in terms of the probability distribution, the likely successes, even if this was true, in terms of pi hat was the actual pi, is going to be very small. And so I am concerned about the standard normal approximation for here. I don't want to conclude that an observation is poorly fit by the model just because it has one less success than if it had one more, I wouldn't have this wouldn't be brought out to me. I didn't say all that very well. Are there any questions? Okay, silence means you completely understand it. So, are there any questions? I think this is just a good example, though, of how it is difficult to understand how well the model fits because of the problems with these distributional approximations. Okay, so we also had number 10 here. Well, 24 out of 29. Yeah, 29 is kind of high. Estimated probability of success, well, it's still kind of high too. But at least I have more observations there. My standardized Pearson residual is negative 2.48, so it's really not too far outside. This doesn't really concern me too much overall. And lastly, with number 15, we see something very similar. I just have a little bit smaller proportion of successes than I would expect from this model. But it's not necessarily extremely unusual. Okay, are there any other ones I want to point out? No, I think that's it. Okay, so are there any questions? So again, the next thing that we would typically do is decide, well, what are we going to do about this? What are we going to do about number 3? And stay tuned to section 5.4 for that. Well, for now, let's go to section 5.3. This is page 561. So section 5.2 tried to identify potential problems that you may have with your model. Section 5.3 focuses on one of these problems. It's called overdispersion. We looked at that a little bit last time. You remember when we were looking at some plots, some residual plots, and we saw that we had a lot more variability in the residuals than we would expect if the normal distribution truly worked out. So we're going to spend a whole section on what to do about overdispersion. Meaning you have more variability in your data than you would expect. This kind of a problem happens a lot more with count data responses than with like the binomial or Bernoulli responses that we had in chapter 2. It can still happen with the chapter 2 stuff, but it happens a lot more with the chapter 4 stuff. So because of that, I'm going to, my lecture notes here are written up with respect to the Poisson regression models. Then at the end of this section, I talk a little bit about, well, what about the chapter 2 models in the context of overdispersion? So now let's think in terms of I have a count response working with Poisson regression. Now, as I've alluded to in the past, a problem with using the Poisson distribution is that the expected value of y is equal to the variance of y. That's just the way that the Poisson distribution is set up. But what can often happen with actual data is that if, let's say that you were to find your sample mean for a data set, you had count responses. And then you also find the sample variance of your data. Now, if a Poisson model truly held, you would expect your sample mean to be close to the sample variance, because that's what's supposed to happen, at least with respect to the expected values and the variances. But what will often happen is that the sample variance will be higher than the sample mean. And that's evidence of then overdispersion. You have a higher variance than what you would expect if the Poisson distribution really held. So let's look at kind of an ad hoc way, first of all, to detect if overdispersion happens. This is with that horseshoe crab example that we saw in chapter 4. And so I just read in my data like we did before. And then I put the data into groups. So the way I'm going to do this is use nested if-else functions. So if-else, test my width. Remember with the horseshoe crab data we had, width was the explanatory variable and the response was the number of satellites around a female crab. If my width is less than 23.25, then put it into group 1. Otherwise, let's keep on going. If my width is less than 24.25, put it into group 2. And then you keep on going throughout. I decided to do 8 groups. So let's go to put my data into groups. I have an object now called groups resulting from that. And I put this in a data frame with my original crab data set. And so you can see observation 1 falls into group 7. Observation 2 falls into group 1. There are other ways to do these kinds of groups. There is a function called find interval. And showing how to do that, it's a little bit easier. If you want to see it, it's in my horseshoe_chapter5.r program that's on my course website. So once I have my data in groups, then what I like to do is find the sample mean number of satellites per group, and also the sample variance. And the way I can do that is to use the aggregate function that we've seen in the past. So aggregate formula equals satellite tilde groups. My function I want to apply to each group is the mean. Do the same thing with the variance. I get some nice group names to make things look nice. And here's what we get in the end when I print everything in a nice little data frame. So in group number 1, for the width less than 23.25, the mean number of satellites per female crab was 1. The variance of all those counts for observations following that group was 2.77. Again, if the Poisson distribution truly worked, we would expect the sample variance and the sample mean to be about the same. Group 2, mean 1.43, variance 8.88. And you can keep on going, looking throughout, and you can see consistently the variance is higher than the mean. Sample variance is higher than the sample mean. This is an ad hoc way to show that we do have overdispersion with this data. Now, of course, you might be thinking, well, why did I choose this kind of a grouping mechanism? Well, there could be other ways to group the data too. That's one reason why it's an ad hoc way. But if you do other kinds of grouping, at least the other kinds of grouping mechanisms that I've done in the past, or in other situations, you still see the same thing. And so while it is ad hoc, I often will start off, if I ever have some kind of count data like this, I will often start off doing something like this. Okay. Now, if the Poisson assumptions were satisfied, just to make sure this is clear again, you would expect the mean.sat column to be somewhat close to the var.sat column. Okay. So why is this so important? Well, what this says then is that if I use a Poisson regression model here, my assumptions are not satisfied for it. Okay. Well, what does it mean then if your assumptions aren't satisfied? Well, it means then the results that you get from the Poisson regression model could be wrong. In particular, we can focus on inferences. So like when I do confidence intervals, when I do hypothesis tests. So in a simple case, let's say I want a 95% confidence interval for beta 1 when I use width to estimate number of satellites. That confidence interval from a Poisson regression model for beta 1 will typically be too narrow than what it should be, because it's not accounting for this extra variability that truly exists in the data. And so what does that mean? Well, if I say that this interval has 95% confidence, in fact, it's probably not. Maybe it's 80, maybe it's 60%. We've talked about those kinds of issues starting way back in chapter 1. And so that's why, if you do have overdispersion, you need to take care of it. Well, how can you do that? Excuse me. The first 3 methods are what's preferable, if you can do them. And then methods 4 and 5, you can go to those if you have no other resort or no other, if you can't do 1 through 3. Often you can't do 1 through 3. So that's why we're going to focus in this section a lot on 4 and 5. Okay, number 1. This is the best thing to do. Well, find an explanatory variable that helps explain the variability in the response variable. So you have extra variability in your response. Well, maybe there's another explanatory variable out there that helps account for that variability. For example, maybe here, in this particular case, let's say if we had access to the weight of the female crab. Maybe that variable would also be good to have in the model along with width. And that will account for this extra variability that's being seen, because width is weight is now accounting for that. So that is the best choice. Of course, though, you need to have access to that additional information. And maybe you do, maybe you don't. Number 2, at the very end of chapter 4, we talked about zero inflated Poisson regression models. Again, there are certain instances with count data where you tend to have more zeros than what you would normally expect if it was truly a Poisson count. Well, you know, if you do have that, and my section in chapter 4 talks about that, you know, basically look, how many zeros do you have? Is it more than what you would expect? Then use that kind of a model. Use a zero inflated Poisson regression model. Number 3, you can use what's called a generalized linear mixed model, where your response is Poisson in nature. This can be helpful in situations where maybe you have, let's say, groups of observations that are dependent on one another in some way. So, for example, maybe with the horseshoe crab data, maybe a certain area of the beach where they're doing their measurements. Let's say you have that additional information that these crabs came from this area, these crabs came from that area, these crabs came from that area. Well, maybe the crabs here are somehow dependent on one another. I don't know enough about horseshoe crabs to know why that would happen, but let's say that they're all dependent on one another somehow. Maybe these are dependent upon one another. Maybe these are dependent on one another. And so what you can do to take into account that dependence is to introduce what's called a random effect into your Poisson regression model. And that's what generalized linear mixed models do. Section 6.5, we'll talk about that, and we will actually do that section next after chapter 5. Now again, if you don't have, if you can't do anything with 1, 2, and 3, then go to 4 and 5. And again, and I don't want to say that 4 and 5 are bad to do. I'm just saying that you should try to do 1 through 3 if possible first. Because what that's going to do is directly address the source of this extra variability. You know, maybe you're missing an extra variable, for example. But if you can't get at that kind of stuff, can't get at that, maybe that additional information, then you go to 4 and 5. And 4 says use what's called a quasi-Poisson regression model. And basically with this is that, you know, you can guess this from the name quasi, you're kind of doing the same things with Poisson regression, but not quite. And so we're going to spend some time talking about that shortly. Another alternative is to use what's called a negative binomial regression model. You know, from another course, you might have heard of a negative binomial probability distribution. Well, instead of using a Poisson distribution for your regression model, we're going to use a negative binomial distribution instead. And this distribution can help account for this extra variability that's potentially present. Okay. So let's talk about detecting overdispersion. You know, we talked about an ad hoc way already. Here are 2 other ways to do it. One that we've already kind of talked about. And there's actually going to be some more ways that we will see once we talk about these different kinds of models. So first of all, you know, if you have overdispersion, you know, you might think in an overall goodness of fit statistic, that's going to be evident, meaning that deviance divided by df, the degrees of freedom, that statistic is going to be large because you have, you know, more variability than what you expect. And we already saw some residual plots in the past where we saw what that meant, that, you know, you have larger residuals consistently throughout your data than what you would expect. And so that should be evident then with a deviance divided by degrees of freedom statistic. You know, it's past our threshold that we've set. And now maybe I don't need to put this again, but again, as I just said, you know, maybe you might have a standardized Pearson residual versus y-hat plot that looks like this, where, you know, consistently kind of throughout you're having these issues, this extra variability in the residuals if a standard normal approximation truly held. Well, let's take a look at our horseshoe crabs and satellites example. Let's look, do I have overdispersion? So let's estimate the model like what we've done before with the GLM function. So with, again, explanatory variable, satellites, the response. So I estimate my model, and let's calculate deviance divided by degrees of freedom. 3.32. Again, the farther from 1, the worse the fit of the model. My thresholds, 2 standard deviations above 1 is 1.22. 3 standard deviations is 1.32. So I am way above these thresholds. This is indicating that this model actually fits poorly, which could be due to the overdispersion. How about a residual plot? So what I do is I get all my predicted values out, my mu hats, let's say. I find my standardized Pearson residuals using the our standard function like we've done before. And then I plot on the x-axis mu hat, y-axis standardized residual. I put in my nice little threshold lines, and this is what I get. So what do you think? Do we got problems? That's not a rhetorical question. It should be an easy question. I know all of you want to say it. Yes, we do have problems. Look at all those observations that are above +2. Note that, though, it's not on the bottom end there, unlike what I showed you on the plot on page 564. But that's okay. This can happen. This can happen with discrete data like this. But we see this consistently for the mu hats. We see this extra variability, at least on the positive side. Now you might be thinking, or you might be saying to yourself, well, I don't see anything up there. What do you mean it's consistently across the whole plot? Well, you only have 3 observations here. So you just don't have enough observations to see it on the higher mu hat side. So that's why I focused on this part. I didn't draw that very well. Let me just redraw it again to make sure that you don't get a misunderstanding. I'm talking about that part. That's what I'm talking about. Overall, we see that we have 10 residuals out of 173 that are above the 3 threshold. And that translates into about almost 6% of our observations. So you see a little bit of some blue lettering there. It's just because it was formatted poorly for some reason in my notes. But the text is exactly the same. Now, how many observations would we typically expect if I had 173 observations? How many typically would we expect, outside of plus or minus 3? We would expect about a half of an observation to be outside that. And we have 10. And so we have a lot more than what we would expect. So this is evidence of overdispersion. So let's look at what we can do. So this is that method number 4, the Quasi-Poisson regression models. Okay, so it's going to take a little bit of development here to get to the main point. Now, if you remember when we do maximum likelihood estimation, we find the log likelihood function. We take the derivative of the log likelihood function with respect to the parameter that we're estimating. And let's say that I have, let's say, p+1 betas in my model. So that means I have to take p+1 derivatives of my log likelihood function, 1 for each beta, set those equal to 0, and then use numerical iterative methods to solve for the beta hats. That's how we do this. Well, whenever you set any kind of function equal to 0 and you solve for like a parameter estimate, the thing that you're setting equal to 0 is called an estimating equation, because you're using a particular equation to estimate something. We'll come back to that terminology shortly. Now, way back long ago, I don't remember at that time back in 1974, but then again, I wasn't very old. Wedderburn suggested using what are called quasi-likelihood methods to find parameter estimates for a generalized linear model. So just in general, not just for Poisson regression models, but just in general, use these quasi-likelihood methods. And the reason why it was called quasi was it was based upon the likelihood functions that we've seen before, but with less assumptions associated with them. So in particular, with respect to Poisson regression, we're not going to say that y is distributed Poisson anymore. Instead, we're just going to make the following assumption, that the variance of y is equal to the expected value of y. But to help issues with potential issues with overdispersion, we're going to add a parameter. We're going to call it gamma. So now we're going to estimate our model in a very similar manner to what we did before. But we're going to allow our variance to be different from the expected value of y. So if gamma was equal to 1, well, we get what we did before. But if gamma is greater than 1, oh, that's going to help us take into account overdispersion.
Is it possible to have gamma less than 1?
It is possible, but it doesn't happen very often at all. So you could actually have under dispersion. I've only seen that once in my life. Okay? Okay. Let's get back to this idea of estimating equations and then use this Wedderburn's idea with it. So for Poisson regression models themselves, the estimating equation, meaning that derivative with respect to a beta of the log likelihood function set equal to 0, that function before equal to 0, one can show mathematically that it ends up being of this form here. The log likelihood function does. So sum over all your observations, take y minus mu. So remember what mu is. That's where the betas are located, times the particular explanatory variable that's a coefficient on the beta of interest, times mu again, divided by the variance of y. With Poisson regression, remember the variance of y would be equal to mu exactly. So this here becomes mu. This also then cancels out. And so that this is actually what your derivative of your log likelihood function becomes. When you're working with, working with the derivative with respect to one of the betas. You can actually mathematically show that. I'm not going to ask you to do that though. So then with Wedderburn's idea, he says, okay, well, why don't we just start with this here? But we make some changes, or make one change. In particular, how will we change this variance of y to be now gamma of mu instead? So then things simplify a little bit. And he said, okay, well, let's just use that now for our estimating equations and find our beta hats based upon this. And those beta hats then, they're not maximum likelihood estimates. But they are estimates from an estimating equation that you can use for Poisson regression, essentially quasi-Poisson regression. That's how they come about. Now what's even really cool, what's even cooler about this idea is that notice what happens when you set this equal to 0. What's the first thing that you could do to simplify it? Get rid of that gamma, right? And so now you're left with what you had before. So the beta hats that you get from a quasi-Poisson regression model are going to be exactly the same as from a Poisson regression model. Exactly. So, well, what about this gamma? Gamma is a parameter. We're going to need to estimate it. And typically what's done is, I'm going to go down to number 4 here. Do note that there are some blue, unfortunately some blue stuff here. That I have a lowercase m in my notes, I think, and that should be an uppercase m. What's typically done is gamma hat is set equal to your Pearson statistic that we saw for that goodness of fit divided by m minus p tilde, where p tilde, and again this is the problem with some of our notation here, is the number of parameters that we are estimating, number of beta parameters, I should say. So that's how we can get an estimate. Okay. So we've talked about 1, we talked about 4. 2 is very interesting. And so the estimated covariance matrix for the beta hats, you still find it in the same way as what we've done before, where you take the second derivative of the log likelihood function and so on. And it ends up being exactly the same as what we had before too, except for one little thing. All the elements of that covariance matrix are multiplied by gamma hat. Gamma hat's going to be typically greater than 1. And so what's the effect then on your variances that you're going to have in that matrix? It's going to cause them to be larger than what they were previously with just a regular Poisson regression model. Again, the reason why that happens, perhaps I'm overemphasizing, it's because of the overdispersion. You have more variability in your data than you would expect. But where does that more variability show up? It shows up in your variance of your parameter estimates. What about various diagnostic measures like standardized Pearson residuals? Well, pretty much exactly the same as before, except for now that gamma hat pops in there. What about your negative 2 log lambda statistic? Well, we use that for likelihood ratio tests. Well, we're not doing exactly likelihood ratio tests here anymore, because we don't have that underlying Poisson assumption now behind all this. But what we can do is this. We take the negative 2 log lambda. You still can use it to do a hypothesis test. We have to divide it by gamma hat. And instead of using a chi-square distribution, now we end up using an F distribution, where the numerator degrees of freedom is Q, denominator is m minus p tilde. Large values indicate evidence against the null hypothesis, just like before. So for now, we're just using a different distribution. Profile likelihood ratio intervals can be found as well. I guess it would probably be good to call these like quasi-profile likelihood ratio intervals. Well, what about the AIC? Well, the AIC in any information criteria, again, is based upon your parametric assumptions that you're making before, meaning y is distributed Poisson. Again, we don't have that now, so we can't use the AIC exactly. Instead, what we can do is use a measure called QAIC, quasi-AIC. And all it is AIC divided by gamma hat. And you can still make comparisons amongst models that are estimated by Quasi-Poisson from this Quasi-Poisson procedure. Note that you should not compare let's say like for example the Quasi-Poisson model that we're going to fit shortly for the horseshoe data. You should not compare that QAIC to the AIC from using just regular old Poisson regression. That you can't do that. You have to stay within the quasi family of models to make these comparisons. The lower the QAIC, the better the model. Also, there's another issue here. For every model you could estimate, gamma hat could change. And because of that, then, what you should typically do is pick one very large model. Let's say you have 10 variables available to your data set. Pick maybe one large model that has maybe all the variables in it. Get your gamma hat from that. and then estimate all these models, all the models of interest that you may have, using the Quasi-Poisson procedure. And then for every AIC that you get from those models, divide that by that one gamma hat that you got from the large model. That way you can make a fairer comparison. Page 313 of my book discusses that in more detail. Okay, so let's take a look at how we can estimate one of these models. We can use the GLM function still, so that's good. The only difference is, now for the family argument, we specify Quasi-Poisson. It's the only difference in the code. We can use the summary function to summarize the estimation or the fit. Notice here, for example, AIC is given as NA, not available. My parameter estimates, and this is shown on page 572, my parameter estimates are exactly the same as what we had with our original Poisson regression model. What has changed is the standard error column. So, the estimated square root of the estimated variance of beta hat 1 is now 0.03562. On page 573, I show what we had before with a regular Poisson regression model, 0.01996. So we can see that the standard error has almost doubled. To emphasize then how the standard error is calculated in comparison to before. Now remember, your previous covariance matrix was multiplied by gamma hat now. So if I take our standard error, the square root of the estimated variance that we had before for beta hat 1, and I multiply it by the square root of, and sorry I forgot to mention this, the square root of gamma hat. I'll show you where you can find that shortly. If you multiply that out, guess what you get? 0.0355, which is exactly the same. Well, there's probably just some small numerical errors there. So that's how that's coming about. Now, what are the ramifications then of having this larger variance for beta hat 1? Well, for example, for a wald test or a wald confidence interval. If I have a larger variance, what's going to happen? Well, confidence interval is going to be wider. What's going to happen to the test? You'll be less likely to reject. Maybe you should think of it the other way. If I didn't do this before, my interval would have been too narrow. If I didn't do this before, I would be more likely to reject incorrectly because I didn't take into account this larger variability. Okay. So also back on page 571 now. Also in my output, you see something called dispersion parameter for Quasi-Poisson family taken to be 3.18. That is my gamma hat. If you want to find your whole estimated covariance matrix, just like what we've done before, you can use the vcov function to do that. And I already said this, but if we wanted to compare it to what we had with a regular Poisson regression model, what we can do first of all is extract from the summary object my gamma hat. So what I'm highlighting here in yellow is my gamma hat. So there's a dispersion component of the list given to us by sum.fit.quasi. If I multiply that by the covariance matrix that we had before, notice that these two are all equal. What about a likelihood ratio test? Well, let's say I use the little ANOVA function. And similar to what we've done before, we say mod.fit, and then now we're going to put quasi. But now we need to specify, hey, or you need to use the correct distribution here. So we need to say test equal f. In my output then, under where it says deviance, here's my negative 2 log lambda. And then this f is negative 2 log lambda divided by gamma hat. Remember, gamma hat was about 3. So I take 64 divided by 3. What do you get? Well, about 20. Using an F distribution approximation, we get a very small p-value still with this case. Not as small as what we probably would have had before. I don't remember what it was before. Saying that there is strong evidence that width does matter. We can do a similar thing with the capital ANOVA function as well. What about a walled confidence interval? So I'm 95% confident that beta 1 is between 0.094 and 0.234. That's a walled confidence interval. Again, I use confident.default to get it. I can then use that to find my PC. Remember that from chapter 4, my percentage change. 9.88 to 26.35. Previously, my profile likelihood ratio interval for the PC was, this is on page 573, was 13.28 to 22.51. That was for a regular Poisson regression model. So we can see again the effect that accounting for the overdispersion has on this. Causes the interval to be wider, which is what we want to be correct. We can do the profile likelihood ratio interval as well. We get 9.81 to 26.26. I'm sorry, this number that I had put in a rectangle here should be directly compared to the profile one. So the 13.28 to 22.51 was the profile likelihood ratio interval from a regular Poisson regression model. Let's look at page 574. Here's using similar code to what we've done before, so that's why I don't have the code here. Here's the new standardized Pearson residual plot versus mu hat. Does this look better than what we had before? Yes, it does. And we still do have some things up here. Maybe I don't like that too well. Well, I should say maybe. I don't like that. But definitely the model's better than what it was before. I am not worried. You mean you kind of see a slope down here? To some respect, that is due to the discreteness of the data, especially for the lower values of mu hat. Because we're dealing with count data here. You have zeros, you have ones, you have twos. That's why you're seeing some of that. Maybe I'm a little bit biased by what I know about this data set. There are actually other variables available, and those other variables can help there. So I am a little bit concerned, but I don't think it's necessarily, without knowing about those other variables, I wouldn't necessarily be have strong concerns, if that makes sense. There are always going to be, you're going to see some trends due to discreteness. When I was talking about trends, before, I'm more like something very, very obvious. Like, maybe you see, if we only have these red dots here, I see something like that. Are there any other questions? Okay. So that's one way to handle the problem. Here's another way, using a negative binomial regression model. Now, I would imagine that a lot of you have seen negative binomial distributions before, but I also imagine a number of you probably have not. The negative binomial, as you might guess, has some qualities similar to a binomial distribution. So we have a probability of success parameter, pi. And you can see, just from looking at this distribution, you can see where pi falls. Kind of similar to what you saw with a binomial. We also have this combination out in front. Rather than the number of trials, choose the number of successes. Instead, it's a little bit different. Y here is, let's say, the number of failures before the kth success. We take y plus k minus 1, choose y. Notice pi is raised to the number of successes power, and 1 minus pi is raised to only the y power. One of the reasons, well, there's a number of reasons why this negative binomial distribution works out well for us. One is, notice what's missing on the right-hand side here. Y is equal to 0, 1, 2, and there is no upper bound. So my random variable, similar to what we have with the Poisson distribution, my random variable y here is a count. It's a non-negative integer, and there's no upper bound to it. So that's one of the reasons why this can be very helpful. Another reason is that we can you can say parameterize our setup here. We can rewrite our Poisson the negative binomial distribution like this, where everything remains the same on terms of that combination. But instead of having pi, you can rewrite everything so that you have k divided by mu plus k, where mu is the expected value of y. And then you also have 1 minus k divided by mu plus k. Don't worry about the mathematical details behind it. One can do that. And the reason why it's good to think of a negative binomial in this light is because of this. The expected value of y, when I write out my distribution in this format, is mu, just like what we have with the Poisson. But look at the variance. The variance of y is mu plus mu squared divided by k. So it's not just mu like we have with the Poisson. Instead, there's a little bit of extra stuff there. And that allows then your variance to be larger than what you would normally have with a Poisson. That's why we like this distribution to handle overdispersion problems. Well, let's look more closely at that variance, in particular k. Notice that as k gets smaller, what happens? That variance gets larger because we're dividing by k there. So as k gets smaller, I have more overdispersion in comparison to the Poisson setting. As k gets larger, notice what happens. That mu squared divided by k goes to 0. And thus I get closer and closer and closer to the regular old Poisson setting. So this k here is really helping us control the amount of overdispersion that we have to deal with. We will want to estimate k, just like we wanted to estimate gamma for the quasi-Poisson setting. So quasi-Poisson, negative binomial, both allow you to have a larger variance. It's just how they take care of that larger variance is different. We'll talk more about comparisons between the two later. Now, since I do have this underlying negative binomial distribution here, I can do everything again with maximum likelihood estimation, just like what we did with regular Poisson. So I can still have likelihood ratio tests, all that stuff. So that's good. I can still use information criteria to choose between models. Let's take a look at an example. Again, horseshoe crabs and satellites. The GLM function cannot be used, I guess, directly to estimate these models. Instead, what we can do is use the glm.mb for a negative binomial function that's in the mass package. Again, the mass package comes with your default installation of R, but you do need to say library mass first before you use functions from it. So, I'm going to put the results from fitting my model into mod.fit.mb, use the function glm.mb, formula equals satellite tilde width, and I say link equal log. So notice the syntax is a little bit smaller here because we have smaller choices amongst the possible models that we can estimate with this function versus GLM. The output is given in a very similar format to what we had with GLM. Here is my beta hat 0 and beta hat 1. These are not the same as what we had with the Poisson regression or quasi-Poisson regression models. They typically will not be. Here is my square root of the estimated variance of beta hat 1, 0.044. Here is my estimate of k. Let's call it k hat. I'm sorry, that's not k hat. That is 1 divided by k hat. Excuse me. This function just works a little bit different from our notation. So k hat then is, this is actually shown on page 577, 1.1. So 1 over 0.9. Notice that we do have an AIC given. R cos 1 over k theta. It's just how they do everything. Notice that what you're given in the output is this estimated square root. I'm sorry, this square root of the estimated variance of this theta hat. Theta is 1 over k. So what this model is saying then in terms of the variance, the variance is for a particular width, mu hat plus 0.9 times mu hat squared. And again, notice how that variance is going to be larger than just saying mu hat itself. How about we do some comparisons between the different models? So what I did was I decided to print off the estimated covariance matrix from the regular Poisson, from the Quasi-Poisson, and now from the negative binomial. Focus on the variance for beta hat 1. Notice how both Quasi-Poisson and negative binomial have larger variances than what the regular Poisson gave us. And it just so happened in this particular case, the negative binomial is greater than the quasi. That's not always going to happen. It just did here. And we can compare in terms of standard errors as well. So I do some just organizing stuff. You can look at the details of the code on your own. So we just saw in the output the standard error from the negative binomial to be 0.044. Notice that's a little bit larger than what the quasi gave us, and definitely larger than what the just regular Poisson regression model gave us. So we're basically out of time, but again, think about what's going to happen now with this larger standard error, this larger variance that we have. What's the effect on inferences? Well, again, larger confidence intervals, for example. Okay, we are out of time. Are there any questions? Okay, and that's it for today.